Hello world. So I am back in a moment. I wanted to make... Oh, you can't hear me if I do that. Um, just wanted to make a video with some solutions to this week's, or I suppose this month's, problems. Let me show you. So I think last time I posted a video for like 40 through 49. So we're going to start with 50. I'm going to go through 50, 51, etc. up through 59. And I'll leave 60 for next month. So yeah, let's hop to it. So 50 is actually kind of the tough one. I mean, it's not that hard, but it's confusing if you're not familiar with complex analysis. It's a little bit tricky, but not too bad. Yeah, so this is 50. We're going to start with that. So in all these things, whenever you're talking about complex variables, you could use polar coordinates as well. Not. I hadn't thought about doing this in polar coordinates. I wonder. Anyway. But in any case, you're usually thinking of complex variables as like there's a real component in this direction, and there's an imaginary component in this direction. So you've got x in the real direction and y in this imaginary direction going up. So every complex number is in this plane, and you're thinking of each point. If you're using Cartesian coordinates, you just immediately do this expansion. You just immediately say, all right, z is x plus iy, and then you're able to do algebra on this just the way you always would. The only catch is that I is the square root of -1. So you want to watch out for this property also. Whenever you square I, you'll get -1 back. So that's a little funky, but other than that, it's usually pretty straightforward. Another way to do it is to say that each point, you can use polar coordinates. You can say the distance from the origin is the radius. Call that r. It's a positive amount, And then there's an angle. It's measured from the x-axis being the angle 0, of course, and then you just go counterclockwise. So like if you had a number that was purely imaginary, this angle would be pi/2 or 90 degrees. You'd be going straight up. I drew it. It kind of looks like it's 45 degrees, this particular random example. So this can be helpful. I hadn't done this problem. So the question that we're working on with 50 is to show that if you take the magnitude of e to the z squared, it'll be bounded by e to the magnitude of z squared. And this is actually kind of reasonable if you just think about it, because like this amount has pretty much got to be bigger than just z squared. With z squared, you can imagine there might be some cancellation, because when you square I, you get a negative, so it's conceivable that there's a bit of subtraction going on here. But over here, there really isn't. And then another thing to point out here is r would be the magnitude of z. Like when you take the magnitude of this, you get magnitude r times magnitude e to the I theta. The e to the I theta is just a circle with radius 1. So here, r is the magnitude of z. So like, right-hand side here is e to the r squared. The left-hand side is not. It's but I guess it's easy to think that it is. If you're using this notation, then z squared is, this times itself. I want to just say this. It almost looks like they're the same. Something fishy going on? Oh, because we're taking e raised to this. That's a little different. You see what I'm saying here? If you look at e to the z squared in these polar coordinates, I didn't do it this way. I'm not going to do it this way for my answer, but I was just thinking about what would happen if you tried, if you were all primed up to think of them only in polar coordinates, what would happen when you try to prove this result? Well, z squared looks like r squared, but then there's this extra term, this e to the 2I theta. So you're getting e to the r squared, but then you're also getting e to the 2I theta right there. So then I guess we have big question mark, like, is this less than e to the r squared? So for instance, if theta was 0, you do get equality. If you chose z so that it's just a real number, it's just on the real axis there, then you do get theta being 0 or pi. Either way, this works out to be, actually that's a problem, right? Anyway, if you look at pi over 2, this e to the I pi is -1. And so you're looking at e to the negative r squared, which you can see is definitely less than e to the r squared. So this term matters. This angle absolutely affects the size of z squared. It doesn't affect the size of the magnitude of z squared, like absolute value of z squared, but it does affect, this thing. So we're seeing that it's still kind of true, but it's a little frustrating because you can't just apply the absolute value in this exponent. You can't just make this go away and say, okay, it's equal to e to the r squared. It's just not true. This is changing. This r squared is a real number, but this part has both a real and an imaginary part. So it's changing the size of this exponent. It's potentially scaling it down. I realize it's a little confusing because if you took the absolute value of that, you just get 1. So it might feel like it's not really changing r squared, but it is. It's, if you want to, you can use Euler's identity to say this is cos of the angle plus I sine of the angle. So you could split it up that way. And then the magnitude of this I sine part, that part's 1, but you've still got this cosine of 2 theta. So I guess what I'm saying is, by Euler's identity, this right-hand side is e to the r squared cos 2 theta. That's the magnitude you would get. Wow, I guess we could prove it this way. This is a little faster than what I was going to do. If you're comfortable with polar coordinates, this is like immediate. We're basically done. So I realize I'm probably glossing over a little bit, right? We were taking the magnitude of this, and I've got r squared times I sine 2 theta. So that's this whole thing is our left-hand side. But I'm saying e to the I whatever, that magnitude is 1. So what you're looking at here really is just this part out front, e to the r squared cos 2 theta. And we're done because cos, of course, is less than or equal to 1. So we immediately get that this is less than or equal to e to the r squared. And we're done. That's what we were trying to show. So it's actually, I hadn't thought about it before in polar coordinates, but it wasn't bad at all. Anyway, I was going to do this in Cartesian coordinates, just regular rectangular coordinates. In that case, what happens when you take the magnitude of z squared, you're taking this coefficient squared plus this coefficient squared. What I'm saying is z squared is, here I'll write it another way. Often early on in complex variables, to make sure that you know that this is true, if you dot if you multiply z by its conjugate, meaning here's z, and its conjugate is x minus iy, right? If you multiply these together, just regular algebra, FOIL it out, and you use this fact, this identity, you'll get a formula like x squared plus y squared. So that's what everyone knows the magnitude of z squared is. So here you get x squared, you get the negative of I squared y squared. I'll just do it slow. You get minus iy squared. Then you have these, well, you have these cross terms, but they cancel out because we took the conjugate. So you have xiy, but you also have minus xiy. So those two cancel out. So I'll go ahead and write them, but they're not really there. You got plus ixy, you've also got minus iy times x. So those are gone. And this is I squared, which is negative 1. So you're actually getting x squared minus negative 1 y squared. You're getting this, which normally I wouldn't even bother to write any of that because this is such a common thing you see early on in complex variables. But yeah, so what everyone kind of knows, when you write in Cartesian coordinates like this, the magnitude of z squared is the real component squared plus the imaginary component squared, meaning x squared plus y squared. That's the magnitude of, that's this distance squared. You know, maybe you're used to that from trig or I don't know, but it's just the Pythagorean theorem. It's just this leg squared plus this leg squared is hypotenuse squared, is what this statement says. Okay. So I know that right-hand side. This right-hand side is e to the x squared plus y squared. The left-hand side is a little gorier, right? Because it's not the magnitude of z. So let's look at what z squared would be. To think about the left-hand side, let's first look at the exponent z squared. Now this time, you don't get any cute cancellation, unfortunately. If you're just squaring this and there's a plus in both factors, that's a little annoying because nothing cancels. So what we're gonna get is x squared, sure. You get ixy and another ixy, and then you get plus I squared y. So I'm gonna do it slowly again. But then over here we get ixy plus ixy. That's 2, should just written like this, I times 2xy. So here's the imaginary component of your answer. And this stuff's going to work out to be the real component of your answer. When you square I, you get negative 1. So that's actually this is the real part of z squared. And this, 2xy, is the imaginary part, or the imaginary component of z squared. But this is the real part. This is real z square, and this chunk is imaginary z square, just to use some notation that they usually use. Which means when you take e to the z squared, that's our left-hand side here, when you take e to that, you're really getting e to all this stuff that I just wrote down. So you're getting this part, and then you're getting e to the I times 2xy. But now we want to take the magnitude of this, magnitude of e to the z squared. So it's the magnitude of this times the magnitude of this, but the magnitude of e to the I anything, e to the I theta, is going to be 1, again, by the Euler's identity, or yeah, that's pretty much it. So e to the I theta just kind of moves you around the unit circle. You pick an angle theta, e to the I theta is just, the magnitude is 1. I'm not saying it's equal to 1. It's equal to a point on the unit circle. So if the angle is 0, then that's 1. If the angle is pi, then that's negative 1. But in magnitude, it's always 1. It just moves you around the unit circle, just like cos theta, comma, sine theta. Those are the points that you get when you look at e to the I theta. So this is 1 in magnitude. When you take the magnitude of this, you just get this real part out front. And now I'm saying we're pretty much done, because we wanted to show that this is less than or equal to e to the z, magnitude z squared. And we said magnitude z squared is this. So we're basically just asking ourselves, is this true? And it is, because negative y squared is less than y squared. We could have had a problem if this was just y, if this was just a single, but because it's squared, you know that's positive, that quantity. So if you're subtracting that quantity, it's definitely less than if you're adding that quantity. So this is true because, first of all, e is an increasing function. But anyway, it's true really because negative y squared is definitely less than, or maybe equal if y was 0, definitely less than y squared. And this is only totally valid because y squared is positive. Or I should say non-negative. Could be 0, but whatever. Besides that case. Right, so if we had something like, if this was just like a, that could be a problem because a could be negative and then this is backwards. But y squared is never going to be negative, so it's true that this is always less than that. That's the way I had done it. If you happen to be looking at the solutions on the website, you'll see okay, so the way that I had done it was using Cartesian coordinates when I did this previously. But that was it. That was my long-winded explanation of number 50. Still not too bad, even though, you know, we're talking about complex variables, so it can seem pretty confusing. All right, let's look at 51. It's a pre-calc problem. It says, find the x and y intercepts. What's the domain? What's the range? Let me blow this up for us. So first of all, a y-intercept occurs when x equals 0. Like if you picture a graph of something, when x equals 0, it intersects the y-axis. There's actually only one, if it's a function, there's only one time that that happens. So you find it by simply letting x be 0. And here we're going to get 3 times 0 plus 10, take the absolute value, then subtract 2. So we get 0 comma some point. In this case, it looks like 10 minus 2 is 8. So it hits up at 8. Then let's see, the x-intercepts, kind of the other way around, is what happens when y equals 0. Now it's conceivable there's a few of these points. These are also called the roots of your function. But it's going to be something comma 0. So this is the one that takes a little bit of work. So if I'm working on the x-intercepts, I'm going to let y be 0 in my equation. And we're going to start doing some math, start doing some algebra to figure out when that happens. If I add 2 to both sides, we're getting 2 is absolute value of 3x plus 10. And this is where it's going to get a little weird. So you need to know another formulation of what an absolute value is. Basically, when you take the absolute value, it either negates the stuff or it doesn't. So if 3x plus 10 is already positive, it does nothing. But if 3x plus 10 is negative, it negates it. Another way to do this, so what I'm saying is we're going to drop the absolute values and we're going to put a plus or minus in front of this stuff. So one way to think of it is like, oh, it's this. And then you have 2 branches to follow, like 2 is the positive or 2 is the negative. But this is always a little sloppy looking. Usually what I'll do instead is put the plus or minus on the left-hand side. It's the same equation, right? If I just multiply by negative on both sides, that'll take care of the negative branch. And if I multiply by positive 1, well, that does nothing. So because this is a little sloppy looking, what I normally do is I'll drop the absolute values, and I want to put a 2 on the right? But I want to put plus or minus 2. So that's going to give us the same results. We still have to do 2 equations. We have to do one case where 3x plus 10 is 2, and we have to do some algebra again, the other case where this is negative 2. But you can see as long as you put this in parentheses and we're careful about distributing the negative sign, this is the same. Like doing this case is the same as doing 2 equals the negative of the left-hand side, of course. So we're just going to do it my way, I guess. If I subtract 10, we get negative 8. And over here, if I subtract 10, I get negative 12. So we've got 3x is negative 12, or 3x is negative 8. And now you can just divide by 3, and those are your answers. So x could be negative 8/3. That's one solution. And another one is x is negative 12/3, or negative 4. So if you were trying to plot these points, like to picture what this looks like, what's 8/3? It's almost 9/3. That's almost 3. It's 6/3 would be 2, right? So it's between negative 2 and negative 3. And it's closer to negative 3. It's like negative 2.66 or something, right? So like we've got 1, 2. I realize the scale is not the same. Sorry about that. But this is 4. That's a root. We said negative 4 is an x-intercept. And then 2 point something, right about here, is another one. The domain we can do, so the rest of the question, let me pull it up again. So we also got to find the domain and the range, right? Domain you can just do directly. Sometimes you have to memorize, like if it's a square root or something, sometimes you need to know a little bit about the function. I'll bring that up in a moment when we talk about the range. But in this case, you basically are asking yourself, like, are there any values of x for which this stops making sense? And the answer is no in this particular case. Like, if you plug in some negative number, like negative 100, you get some stuff in the inside, like negative 300 plus 10 or something. But you can take the absolute value of anything. You can take the absolute value of a negative number, a positive number, 0. So you're not going to have any issue with any value of x, and that's why I'm going to say negative infinity to infinity for my domain. The range is where you really need to have, usually you learn this in like a pre-calc class. You probably want to have half a dozen functions or so off the top of your head, like the absolute value shape looks like this, or x squared looks like this, or of course straight lines, lots of straight line examples. Square root, you want to know that shape. Cubed root is kind of the same thing except that it's odd. So at some point you memorize about half a dozen different shapes, and that'll start to help you get the range. If I look at this stuff, it's giving me some value, but I know this shape in general from the absolute value of x. These are what its y values look like. It gives us this little triangle shape, right? It's got a cusp at 0. So little, I don't know, sharp turn there, right? We're taking that kind of function, and then we just subtract 2 from all of the y values. So it's going to give us a shift downward of 2 units. So I now know that that's my minimum. And since we already drew these 2 x-intercepts, it's like kind of right in the middle of those 2. So now I know that my shape must look something like this. And that's okay. So that's giving me the range. Again, to get the range, you would have had to have memorized a handful of different functions. Our minimum is negative 2. It does attain that minimum, and that's why I'm going to put a square bracket here. And it just goes up without bound. It gets as large as you want to go. You can get as big a y value as you want, so that's why I'm going to put an infinity there. And that's about it for this problem. Let's see where I'm at here. Hey, Max. Welcome in. Yeah, sometimes I do proofs. Right now I'm making solutions for this Math Challenges website. Some of these problems are more advanced, like real analysis questions or complex analysis questions. So those ones might involve actual proofs. But a lot of this is just a lot of this is just crunching numbers on this website. So like it'll be a differential equations problem. You don't really have to prove anything here. You just sort of verify that when you found your solution that maybe it satisfies, when you take its derivative, it satisfies this equation, or like linear algebra, find the determinant. Like this is very just computational. There's no proof on this one. But probably later on actually I might have even had some already. Yeah, this is more sort of proof-based. Suppose you have a transformation that has this property. Is it an onto map? Why or why not? That's kind of it's proof light. Yeah, sometimes there's proofs on the website. All right. I'm gonna need more room for this one. So 52 is we're on to discrete math. These are the previous discrete questions. Speaking of proofs, this was an easy one. This is from basically these just go in order. So this is like week 1, week 2, week 3, week 4. So if you were to take a class on discrete math, this is basically just going week to week. So we're looking at questions now that are sort of like, this was week 5 of a basic discrete math course. This one's pretty straightforward. This is just a probability question. Yep. Yeah, I made this website a few months ago. You can check the notes to see the dates. So I started this back in April 1st. And I've been posting my answers as we go along, So like 27, right. So 27, 27's a quick one because I didn't have to prove this theorem. I'm just sort of citing it. It's kind of, there's a big theorem in linear algebra that's like the rank nullity theorem, or really just the invertible matrix theorem, it's sometimes called, where it's like, oh, the following are equivalent, and they list like 8 different results that are all, some of them are kind of similar to this statement. So I didn't prove that from scratch. I basically just was like, well, if you've got a fixed point, that means a couple of rows are basically repetitions of each other. Yeah, so this was my answer for that one. But I had to cite a couple theorems, otherwise, it would be a very long explanation for that particular one. But this is one that was more interesting to me at the time, because I didn't really remember how to do LU factorizations. There's a handful of different factorizations in linear algebra. When it moves on, this one's not too bad. This is actually, sometimes you'll see this in like a discrete math or in a finite mathematics course. Towards the end, sometimes they'll do stuff like this. Yeah, I know. I didn't remember how to do it at the time, but it's not that bad. But yeah, like if you asked me to do it right this minute, I would have to, I don't know, I'd have to brush up. It would take a minute. But it mostly just, I think for the L part, you just kind of row reduce it and you just do the opposite of whatever. So like here you can see that this is -3 times that. And so the first entry in your, oh, you can barely see it probably. Let me do something real quick. -3 is -1 times that, and that's the number that goes there. Or like 9 is 3 times that entry, so 3 is the factor that you put there. So you're kind of just recording what you would do as a step. So like finding L is not that bad. And then U is just sort of whatever you had there when you did the row operations. So it's like whatever was left after you did this cancellation. But like I was mumbling, yeah, LU factorizations, I don't know how easy it is to remember them when you haven't done this stuff for a couple of years. You'll never forget determinants, right? And you'll never forget row reduction, obviously. And you probably won't even really forget this kind of question, because you're like, wait a minute, how would it fix a point? That's kind of fishy, right? So you have some innate stuff, but then you're like, oh, do this LU factorization. It's like, ah, man, why would I remember? Why would I remember how to do that? Anyway, let me move on to 52 here. Get myself some fresh paper. So let's see. Make this big again. I'm going to jot down, I'll just make a tree or something. Store sells 2 types of flash drives, A or B. And then we seem to know, oh, okay, right away they're telling us the percentages that they actually sell. So like the majority of the time it's brand B, but 30% of the time they sell brand A. But then half of the brand A's are defective, while only like 5% of brand B are defective. Anyway, as you can imagine, the question's going to be, we've got a defective drive. What's the probability that it came from brand A? So I would usually, how well you can read this. There we go. I mean, when you get good at these, I guess you can just write down whatever you want. Like we could say A is the event that brand A was sold. And so we know that probability of A is 0.3. Probability of B is 0.7. And then what they also told us is that given that you're purchasing a brand A device, there's like a 55% chance that it's defective. We'll make D be the event that it's defective. So they told us that this conditional probability is 55%. And for instance, given that you purchase a drive from what is it, brand B? Brand B. Given that you purchased brand B drive, the probability that it's defective, given that it's from brand B, is 5%. So if you already know the formula, these are the numbers you need, you just crunch away and we're done. But usually I'll try to make this, put a little visual here for people. So we know that there's a 30% chance that you took this path, and there's a 70% chance that you took this path. Now, if you took path A, we know that there's a 55% chance of it then being defective. And we'll say the 45% chance, N will be not defective. And then similar branches for path B. It's either defective with probability 5%, or it's not defective the majority of the time, 95% of the time. And it's kind of nice to lay it out in a tree like this, because then if you want one particular result, like you want B and D, just for example, the probability of being from brand B and being defective is just the product, this times that. Now, if I write down mathematically, what we're saying is that this is, by definition, this guy. But if you get used to drawing the trees, you don't have to think as mathy as this, you know what I mean? If you get used to the tree, you can kind of have more instinct for saying, like, oh, it's just this times that, because these are independent things. And so this is 0.7, that's 70% times the 5% chance of it being defective, given that you're on branch B. But either way, you got to realize this, that this is this product. And then the last thing we do is say we're looking for, well, we should probably look back at the question. It says what? If it's defective, what's the probability that it came from brand A? So this is a very typical, let's write it down exactly what it wants. Given that it's defective, what's the probability it came from brand A is what we're looking for. So this is a typical Bayes' theorem type question. You're looking for this, but you've been given sort of the conditions reversed. You've been given the probability of being defective given that you're from brand A, which is obviously, it's not the same as just swapping that. If you've got a defective drive, what's the probability it came from brand A? Well, that's a more complicated answer. But Bayes' theorem says the following. I mean, this is the actual definition. This would be, let's see, the intersection of these two things. It's A and D divided by just D. And then what Bayes' theorem says is that you should expand this just using the definitions. So upstairs, we're going to use just what we wrote here, that this is the probability of A times D given A. But downstairs, you just do this trick where if it's defective, it either came from drive A and it's defective, or it came from drive B and it's defective. So the denominator, you're going to think of it as, let me do this slowly. It's if you're defective, that means you're either in A and you're defective, or you're in B and you're defective. And so then one last step is just use the usual definition for the intersection that we just wrote here. So replace this intersection just like I did upstairs. Replace this intersection with this formula, A times D given A. And that's Bayes' theorem. I guess I'll just write it here. So the top is A times D given A. And downstairs you're going to have that same product. Shows up here, A times D given A. Or B times, basically what we just wrote here, B times D given B. Basically what I just wrote right there. So anyway, if you want, you can just look at the tree too. You can use this definition and say like A and D, and you just multiply the two numbers. So upstairs we get 0.3 times 0.55. And then downstairs we have all the ways that D could happen, which is this or this. And you just sum up those two products. So one of them is for sure going to be this again. One of them is the A case again. So this is not surprising to me at all that I see the same numbers. But then you've also got 0.7 times, and then whatever the probability of being defective given that you're on branch B is, which I guess is 0.05. I think I might have done that one earlier right there. I didn't bother to do the number out. So we're there. Now you just grab a calculator and you're just careful, basically. That's what most people do. Another thing you can do is realize that these are the same, the denominators are the same everywhere. Like if I, like this is 1/100th, and this is also it looks like it's more like 1/10th, but you could also write this as 1/100th. So you're getting sort of 30 1/100ths times 55 1/100ths. You see what I'm saying? Why would I do that? Well, the 1/100th squareds are going to cancel, so you'll have nicer numbers to deal with. See what I mean in a second. This is the same number, right? But 1/100th squared on the top and the bottom, if I factor it out, you're getting this, 30 times 55 over 30 times 55 plus 70 times 5. So I like doing that. You know what I mean? I've done enough of these that I don't like dealing with all these stupid decimals when I grab a calculator. You could also get rid of a 10th here if you wanted. But that's a coincidence that you happen. But you can always do this step, what I just did from here to there. Well, I say that. It kind of depends on what the numbers were, but generally you can always do that. So yeah, let me get rid of a tenth just so these numbers are a little easier on my brain. This is the same as this number. 7 times 5. I just divided everything by 10. So okay, 150 plus 15, right? So it's 165 over 165 plus 35, I guess. Yeah, sure. So 570, so this is 200. So it's 165 over 200. And if we, let me show you what I had for answers on this. So I'm going to move on from there. You could certainly divide it if you wanted. That's a little strange. Oh, I see, out of 40. Right. So this is divisible by 5. I see. 33 times 5. Yeah, that's fine. We can leave it like this, though. I guess if you cared, what is it, 80? It's like 82 and a half. No. Oh, yeah, no, it's 82 and a half. That's right. So it's 0.8. It's 82%, you know. What was the question? We have a defective drive. What's the likelihood it came from brand A? I mean, we buy fewer of brand A, right? Only a third of the time do we even purchase it. But the fact that you've got a defective one and brand B almost never sells a defective one, right? So as soon as you have a defective drive, you're like, oh, this is probably a brand A. It's pretty unlikely that it's a brand B because only 1 in 20 of brand Bs are bad. So anyway, you're looking at this defective drive, and you're immediately saying, well, I know it was less likely to get an A, but since it's broken, this is probably an A. It turns out there's an 82% chance that it's an A. So your instincts would be correct that I've got a broken drive. Half of the drives that A sells are broken. It's probably a drive A, or probably a brand A. All right, let's move on. Mat 53, which is a calc problem. I guess if this is your first time seeing my website, I go in order. So a couple times a week, I post a new problem, and they're all just any undergraduate level question, starting with pre-calc and discrete math, and then calc 1, 2, 3, 4, and then linear algebra and abstract algebra and real analysis and complex analysis. So they're all just undergraduate questions, but they do get harder, obviously, as you get into like linear algebra and complex variables and stuff like that. But even if you're not really a math person, you can definitely handle the pre-calc and the discrete stuff. And if you haven't seen it before, you'll probably learn something. Like that was what we just did was a typical. It's definitely a typical question you would see in a finite math course, which is sometimes you'll see that in discrete, sometimes not. But this is actually still pretty early probability stuff. Like for sure you'll see it in a statistics class. Once you start talking about conditional probability, Anywho, so 53, we are entering Calc 1. This one's very computational. I'll make it bigger so you can see it. Okay, so extremely computational question. So this one's mostly painless. I'm not going to spend much time on this one. You just got another chain rule and your basic power rule stuff. What is that? 5x cubed minus 3x squared. Anyway, let's just do this one quick. So we're looking at 53. It's a calc question. The function is stuff to the 10. Anyway, here goes. Y prime will be. I do the power rule on the outside, like I treat it as stuff. I just keep calling it stuff on the inside, or u. So you get 10 stuff to the 9 times the derivative of that stuff. It's like 10u9 times du dx, or 10u9 times u prime. So we just rewrite the inside stuff. It's like 10 inside stuff to the 9 times the derivative of this inside stuff. You get 15x squared minus 6x plus 2. And I would just leave it like that. There's really no need to try. Obviously, you're not going to expand this to the 9th. No one wants you to use some crazy multinomial theorem or something. That's it. That's it for this one. In fact, let me see. Did I even do any more? There wouldn't be more to do. Yeah, just leave it like that. All right, Calc 2. Do we have room for this? Let's just do it in the back. Let's give myself some more room here. So this is Calc 2. I'll do this one pretty quick too, because if you've seen series at all, these ones are actually pretty easy. The first one looks a little scary at first, I guess, but these are both geometric series. There's like not a whole lot going on here. So this is Calc 2. It's not as scary as it looks. It will get worse, maybe next week. But here goes. We'll do this one quick. So the first thing to notice is that this first one's actually a gimme. It looks a little annoying, but if you think about cosine pi over 2 or cosine 3 pi over 2, it looks like this question was carefully constructed. If you take any odd number times pi over 2, let's see, here's pi over 2, and then here's 3 pi over 2, and then it repeats itself, right? 5 pi over 2, 7 pi over 2. The x-coordinate is 0 in both of those cases, so cosine of those angles is 0. So the answer for A is just 0. It's just a sum of 0 a bunch of times. Yeah, bit of a silly question. The second one, you just kind of, if you factor a fifth out, then it's this. I did that so that the power would match up and I could just write it more cleanly, right? And then we're going to do what I usually call re-indexing. Instead of letting k start at 1, we may as well let k start at 0, right? If you plug in 1, you seem to get 0 there. So this is the same as this series. If we let k start at 0 instead, you could just replace this with k. If that's confusing, though, you could just do a literal substitution. You could say, like, j is k minus 1, and yada yada. J goes from 0 up, and this becomes j. So this is basically all I did. I just replaced k with a new variable. But the reason I did that is that we have a formula for this. This in brackets is a geometric series. You usually write it as 1 over 1 minus whatever the base is. In our case, the base is 4/5. So the stuff in brackets is what I wrote here. We've still got a 1/5 out front. So yeah, just crunch those numbers. 1 minus 4/5 is 1/5. That's funny. It happens to cancel. That's a coincidence, but so we're looking at 1 over 1/5 times 1/5, which 1 over 1/5 is 5, so 5 times a fifth, so we're getting 1. So the answer on B is just 1, like the total, actually. You can't always get, like, here we're just going to say it's convergent, but, you know, we happen to be able to sum these examples. Usually that's not the case. Usually you're just able to say, oh, it's either finite or it's not. In this case, I'm able to tell you the sum on B is 1, and the sum on A is 0, which is kind of a strong result, right? But these are also simple questions. And then C is another pretty quick one. This one's very obvious that it's a geometric of some sort. We're going to write it like 3/2 to the k. We could just immediately do that. But then you can also immediately say diverges, because these terms aren't even getting smaller. It diverges because the base is greater than 1. You're looking at a geometric series like a to the k, where the magnitude of that inside stuff is bigger than 1. That means it's divergent. And if you don't know what the heck I'm talking about, what I'm saying is if you try to add these up, you get 3/2 plus 9/4 plus 27, I guess, eighths, right? Plus 81 sixteenths, yada yada. These numbers are actually getting bigger if you crunch them on a calculator or something. Right, this was 1.5. This was bigger than 2. This is now bigger than 3. This is also bigger than 4, right? So this is actually growing in size. If it was possible for this to be convergent, those terms would at least have to be shrinking, and they're not. So you can call this the divergence test sometimes, but the terms themselves are getting smaller. You could also just say diverges by the geometric series, just facts that we know about the geometric series. All right, we shall move on. 55. Uh-oh, multivariable. Let's zoom in on it. All right, ladies and germs. This one's not as bad as it could have been. Let me show you a previous, here's last week's multivariable question. Compute the arc length, which is also not a bad problem, but you have to know stuff to do this one. You'd have to know the arc length formula, first of all. You have to sort of understand this notation that this is a vector valued function. This is probably a lowercase t, not a bold t. Anyway, let's get back to it. This one is not too bad, actually. This one, I feel like this is just algebra. You could probably give this to a high schooler, potentially, and they might have a clue. They could at least do most of it. At the end, putting it in vector notation, that's maybe where the multivariable stuff comes from, but this one's actually not as bad as it looks. So you have a plane, right? You visualize this as just a plane in 3 dimensions. If you did have 2 different planes, right, intersecting each other, here's my one plane up at this angle, here's another plane coming through it, okay? If they did intersect each other, they intersect in a line. And I guess that was part of the question. It says find the line. But that's kind of fundamental to answering the question, is that you understand you're going to get a straight line answer. Oops, there it goes. You're going to get a straight line. It might not be, I don't know what the angle is going through space, but the point is you're going to get a line. And right now you have 3 variables. So somehow we're going to get rid of one of those variables, and we're going to have only 2. So this is a problem, I think. If you haven't seen multivariable in a long time, this would probably scare you. But first of all, they intersect where all 3 points are equal, right? We need the set of points where Q and R are equal. So I guess that means that the z coordinates in particular are equal, right? So that's the first thing we do, is set z equal to z. So take your first equation and solve for z. Looks like I'm going to get x plus y minus 1. That's coming from the q equation. All I did was solve for z. This is the same as the original q equation. And then on the r equation, we have x plus 2y plus z equals 1, right? So z is 1 minus x minus 2y. So okay, so I solve for z. Well, otherwise, these are the same plane equations that we just had. So set z equal to z. And you'll basically be almost done with this problem, believe it or not. Fidget with this, okay, solve, maybe solve for y in terms of x. That would be smart. But we're kind of well on our way, right? Because this is kind of already a straight line. It's just not in standard form yet. But clearly this is the equation of a straight line, right? If you had something like ax plus by equals c, and someone said, what is this shape? You'd say, that's a straight line. I could figure out what the slope and the y-intercept are if I was forced to. So this is a line. We're almost done, huh? Anyway, let's solve for y. If I add 2y and I subtract x, you're going to get stuff like 3y. Let's add 1 too. I get 2, and then I subtract x, I get 2 minus 2x, something like that. So I'm going to go one step further and say y is 1/3 of like that. Or you could even, I don't know, you could do 2/3 of 1 minus x. It doesn't really matter. This is fine. Okay. 2/3 of 1 minus x if you prefer. We're pretty much done. This is fine. The only issue is I don't know where z is, right? Like I know how y depends on x, but I don't know how z relates to these things. I'm going to have to grab either one of these. I guess I like this. It doesn't matter, but I guess I like this one. So what you could do now is say, all right, we've got an x coordinate, and we've got a y coordinate, and we've got a z coordinate. And x just, one of these has to be a free variable. Usually you think of it as x. So what we could do is let x be t. That's our free variable. T could be negative. So t is just negative infinity to infinity is the domain. Yeah, but y is given by this formula, right? If you have a fixed value for x, this is what the y value would be. So it's 2/3 1 minus t. In fact, we should probably expand that. It's 2/3 minus 2/3 t. I'm going to do one last step after this that'll explain why I'm doing that. And then finally for z, you could actually use either one of these. It wouldn't matter because they're supposed to be equal, right? So z is 1 minus t minus 2y, where y is the thing we just wrote previously. So in big parentheses here, I'll put this junk that we wrote for y above it. 2/3 minus 2/3 t. I'm going to clean that up real quick. Z is, let's see, 1 minus 2 times 2/3. So 1 minus 4/3. And then negative t looks like positive 4/3 t. Minus t plus 4/3 t. Eesh. So 1 minus 4/3 feels like a negative third. 4/3 minus 1 looks like 1/3. That's a formula for z. And the only reason I did all this junk at the end here, I mean, this was complete. There was nothing really wrong with what I wrote, but it also says express your answer as a vector. So they want us to have a formula like r of t is maybe the vector. They want us to have like the sum of two vectors, or that you're scaling a vector. They want you to basically like write a vector and then say we're going off in this direction. They want you to express the line in vector notation. So the way we're going to do that is to say we've got a fixed point plus t times some other point. I said point, but I mean like vector. I mean a vector. So x, the first coordinate, is 0 plus t. That's how I'm expressing 0 plus t times 1. That's our first coordinate. And then the y coordinate looks like it has 2/3. That's our starting point. And we're subtracting 2/3 of t. So I'm going to put negative 2/3 over here in the y component that's being scaled by t. And then finally the z coordinate we said is negative 1/3. That's our fixed value. That's like our y-intercept. I guess it's sort of a z-intercept. But if you're picturing it in 2 dimensions, we've got a y-intercept plus an angle times a variable. Y-intercept plus an angle times a variable. I said angle, I mean a slope. This is like the slope. Anyway, back to the drawing board. There's a fixed value of negative 1/3, and we increase by 1/3 t, so it's plus t times 1/3, and that is it. That would be my final answer on. So maybe that looks a little weird, but that's just vector notation for this straight line. We've parameterized this line. But really the work was not that bad, right? You just set z equal to z. You figure out what the line is. We had this equation for the line. This is the bulk of the answer right here. Conceptually, this is the answer. But then we parameterized it and we wrote it as a vector. That's all. All right, moving on. 56, diff EQ. Let me blow this up for you. Boom. I did do these in the past, so if I get stuck, I can pull up my answers that I might have done them a couple weeks ago or whatever. It's easy for me to forget what the heck I was doing. First order linear. So the first thing you do on all of these is check if it's separable. What I mean is when you have a differential equation that looks like, say, this, if you can divide by y and get something like that, that becomes very easy to do. That is not what we have here, okay? So this is separable, but the example that we're looking at in 56 here is not separable. So as soon as they become not separable, you're going to need some heavier machinery to solve these. What I mean is you're either going to assume you know what the answer is, like you have a model for what y is, and then you solve for the coefficients, or you're doing some sort of heavier machinery, like some theorem that you know. So I'm going to jump right to the point. We need to use a technique called integrating factors. If you're wondering what the heck we're about to do, you want to Google integrating factors. But this is a very standard thing, and it's actually not that bad. If I rephrase what we've got here, it looks like this. And our life would certainly be easier if this function was 0 on the right-hand side, but big deal. We're going to call this g in a minute. This is g of t. But this on the left-hand side, there's a coefficient here. It could have been anything there. It could have been like 3y. It could have been like ty. Could have been e to the ty. We don't know, right? It could be anything there. In this case, it's a 1y. The whole point with integrating factors is that this, on the left-hand side, looks like the product rule. It is the product rule, if you're careful. So we're just going to multiply by a function and say, oh, that left-hand side is the product rule, where this function that we solve for makes it happen. What I mean is, if we were to multiply on both sides, I'm going to see if I can derive this integrating factors technique for you while I do this, okay? Multiply by a function we call mu on both sides. And we're going to solve for mu in a second. But the point is, what would we get? We get mu times y prime plus mu y equals mu times, I'll just call it g, okay? Mu of t, g of t on the right-hand side. Now, normally there's a p here. Is that okay? I should have written it. Usually there's a function p. So that's mu of t, p of t, y of t. And the whole point of this technique is to say, oh, that's the product rule. But like, how is it the product rule? It would need to be that if this is not differentiated, it would need to be the case that mu's derivative is this part, mu times p. So like separately from this, you would have to solve this, but this is separable. Mu prime over mu is p, means that like log of mu is the integral of p, meaning mu is e to the integral of p. And that is what's called the integrating factor. So when you use this technique, the first step that you do is identify p, and then you take this. You get e to the integral of p. And that's your function. That's what's called the integrating factor. Okay, so that's where it came from. It came from just multiplying by mu and saying to yourself, oh, the left-hand side is a product rule. So that's how we get that function. But then we're not done. The cool thing is the left-hand side you said is the result of a product rule. I guess that means that it's ddt of this, right? But the right-hand side we haven't done yet. The right-hand side is mu of t times g of t. So if you want to actually finish the problem now, you're going to integrate both sides with respect to t. You're going to get mu t times yt. But on the right, you'll still have an integral to solve. You have to actually integrate this part. You have to integrate mu times g. And that's it. That's the whole technique of integrating factors. Now we're going to divide by mu, but first you have to do this integral out. So get this general antiderivative, divide by mu, and voila, you're done. You have a formula for y. That's it. Also, keep in mind, when you finish this, we're probably going to have a plus c. You are taking a general antiderivative here. You should probably have a plus c after. So for our case in particular, p is 1. So in our example, let me rewrite it, I suppose. Y prime plus y is sine 2t. What I would say to myself is this is the g function, and p is 1. And so mu is e to the integral of 1. So it's e to the t. You don't need to put a plus c here. The reason is, if you put a plus c here, you're just going to get a constant. It's going to become k e to the t for some fixed k. But we're about to like integrate against that and divide by it, so the k's end up canceling. So it really doesn't matter. So like in this one case, you don't need to put a plus c, because it's all kind of a wash anyway. It is there, but it doesn't matter because it's going to cancel. Okay. So this is our integrating factor, e to the t. And then by our formula here, what we want to say is, the answer is basically y is 1 over mu, which is e to the negative t, I suppose, right? Times the integral of mu g. So take that integral, don't forget your plus c, and then divide it by this guy. So for us, what this is e to the negative t times whatever we get when we take the general antiderivative of e to the t times the right-hand side. Oh boy, that sucks. But anyway, conceptually, that's all we have to do. And then I think there was one last step. I think in our case, we wanted, there's an initial value that they gave us. 0 is supposed to get mapped to 5. But we'll take care of that at the very end. 0 going to 5 is why I'm telling you got to be careful. Don't forget your plus c, is what I keep saying. Now this integral sucks. Maybe I can just do it here. It's just annoying. It's easy. It's by parts, integration by parts, but it's a little bit annoying. So on some scrap paper somewhere, okay, we're gonna write integrate. Let's call I e to the t times sine of 2t. Usually let dv be the hardest thing that you know how to integrate. I don't know if that helps us here. It doesn't really matter which direction you go, as long as you're consistent. We're going to have to do this like twice and then do a teeny bit of algebra to solve it. I'm going to let dv be e to the t, because I'd rather differentiate sine of 2t. It just seems easier. The derivative of that is 2 cos 2t, and the antiderivative of e to the t is just itself. So by parts, we get this integral is uv minus the integral of v du, which looks like it's 2 e to the t cos 2t. Huh. Seems I did this probably in my answer on the site. I might have written this backwards, but it doesn't matter. And I guess we'll see, won't we? So now you've got another stupid integral to do right here, right? So if we did it again with a cos in the way, just make sure that you're consistent. You go the same direction, right? If I make dv be cosine 2t right now, it's gonna undo itself. It's just gonna tell me like I equals I, which is probably not super helpful. Anyway, the derivative of cos 2t, I think that's gonna be negative 2 sine 2t. Antiderivative of e to the t is itself. So this chunk, we've got I is e to the t sine 2t minus 2, and then we got another by parts, sadly, which is why I said this sucks. Minus 2 times what? uv minus integral of v du. Of course, there's another negative there, so when you do minus the integral, it looks like this. And hey, what do you know? That's what we started with. But believe it or not, that's a good thing. So what I've now got is I equals e to the t sine 2t. There's no integral sign there. And I've got minus 2 e to the t cosine 2t. Okay, fine. And then I've got another 2, so this is minus 4. And then that's the original integral we had that I called I. So, oh my goodness, we're almost done. If you add 4i to both sides, you're getting 5 times the original integral is this mess. And this is correct. The reason I'm saying that I know it's correct is I did this earlier. I did this another time where I assumed that the answer would be like alpha sine 2t. Like you could see this and say, oh, you know what? I'll bet it's alpha sine 2t plus beta cosine 2t, right? You should maybe know that when you differentiate sine, you get cosine. Differentiate cosine, you get sine. So you might say to yourself, is this just like some linear combination of sine and cosine of 2t? And you're basically correct. And if you solve that, you'll get 1/5 and negative 2/5 for the two parameters. Okay, so that's why I'm like happy to see these numbers again with the 1/5 involved. But I do admit that this sucks. It's always frustrating when you have to do it twice and like do some algebra to get, nobody likes doing by parts. So what are we doing? So I have a formula that I'm claiming is the answer to this stuff in brackets. Don't forget to put a plus c on it. Our final answer here is that y is e to the negative t times, and then I'm going to, all this junk that I have for I, I'm going to go ahead and copy that, but don't forget to put a plus c. So we've got 1/5 e to the t sine. We've got negative 2/5 e to the t cosine. And that would normally be it, except for possibly plus a constant of integration. And you're almost done. You're basically done with this problem. The e's do cancel, so that maybe clears up some headache. Here's a general antiderivative. Here's a general, oops, damn it, it's gone. Here's a general solution to our differential equation. Right? Remember I was saying this is what I had done. If you had just assumed that this was the answer, you could find alpha and beta. Of course, the problem then is that you can't get the particular solution of y of 0 being 5. That comes from right here. We've got plus c e to the negative t. That's also there, potentially. So that's also, if c was 0, then you just get y of 0 equals negative 2/5, right? So if you do it using integrating factors, like we just did, you'll get this extra term, and then you'll realize, oh, wait, I wanted y of 0 to be 5. That means I want this junk. I want 5 to equal this stuff with 0 plugged in for all the t's. And you'll get negative 2/5 plus c. And there you go. There's your answer for c. And we're finally done with this problem. So 5 plus 2/5 is c. What's that, 27? 27/5. So if I let c be 27/5, that'll be the particular value that gives you y of 0 equals 5. I know, a little long-winded, but not as bad as you might think for a differential equations problem. They've started to get a little worse than they did at the beginning. When separable equations are always nice and easy to solve, but Euler's method, this is a very computational question. That was the fourth week of problems. 5th week of problems was last week, and this is an integrating factors question, right? As soon as you can't separate anymore, if you can't divide by y and move everything that involves y to the left, then it's probably integrating factors, frankly, unless you're able to just guess at the answer. Anyway, I'll move on. That was differential equations. Let's take a look at our linear algebra problem of the week. Might be kind of anticlimactic for you guys, because this so I hope that's not too disappointing. This one's not not too scary. Do I have any room? Oh, okay, I do. But on the other hand, you do have to remember like what changes when you take a determinant. Like what can you do? And I'm always like fuzzy on that. If I had let's do an easy one. If I do like 1, 2, 3, 4, I know the determinant of that is 1 times 4 minus 2 times 3, right? This is negative 2. If you scale a row, if I instead double the first row, well, it kind of stands to reason that I'll have this extra factor of 2 in every single cell in the row, which means there's an extra factor of 2 everywhere. So doesn't this just double my... It should just double. Like if you scale one row by one number, say you scale it by alpha, I think I would expect the determinant of like 2a to just be 2 determinants of a. What do we get? 8 minus 12, which is negative 4, and so it just doubled this, so that's true. But I was saying that it's definitely the case because you've doubled every entry, and when you take a determinant, you're using every entry of the row. So you should be able to factor out that number that you just distributed it in. You can factor it out one time, and that's why there's 1, 2 here. Hey, what's going on, Kenny? Good to see you, bro. So that's one property that I remember, If you change the order of the rows, does that do nothing, or does it negate your answer? Let's see. This is not a proof, I'm just saying, what if I had altered the order of the rows? It certainly shouldn't change the size of the matrix, whatever that means, but does it negate? I can't quite remember. 6 minus 4, it does negate. So if we scale, it's stupid for me to write this, right? Scaling scales the determinant. Altering, what do you want to call it? Swapping rows. Swapping rows negates the determinant. Those are two very basic steps we would do. Now there's a third step that we would do that would be very helpful for questions like this one. What if you add one row to another? I'm just going to write it. Adding a multiple of one row to another does not change your determinant. Wild, right? Why would that be? Well, it does seem plausible, I think, because yeah, it's hard for me to prove it, but let's just do one example. It's hard for me to prove it in words just without any other theory. But because it wasn't like a linear change like we did when we scaled, it almost seems like when you take the determinant, when you do that algorithm, it sort of takes this row operation into account. That was a stupid way to say it. So that explained nothing. But let's just do one example. If I add this to row 2, let's add it twice, okay? Just for kicks. If I add it twice, we'll get 1, 5, and 2 times 2 is 4. We add it, we'll get 8. So I think I added this twice. I added it once to get 4, 6, and then I did it again to get 5, 8, right? Let's take this determinant. We'll get 8 minus 10, which again is the same as the original determinant. So you can see that I believe this. You can see that I believe if I add any multiple of one row to another row, I have altered the original matrix, but I have not changed the determinant at all, weirdly. But notice I added an entire row, like I did a row operation. I didn't scale. If I scale, then you'll have scaled the determinant as well. And weirdly, to me, this always seems strange, but if you swap rows, you just negated. So you got to be careful with swapping rows. But you probably don't need to swap rows. The other thing that I know about determinants is just broadly, you don't see it in a 2x2 case, but how you take a determinant, say I had like 1, 2, 3, 4. That's probably good enough. You know, 0, 1, 0, 2. I'm not going to actually do this one out. I'm just writing some numbers down. Right? So the way that you take a determinant, you might remember what we were just doing, like AD minus BC. But what you're really doing in higher dimensions, of course, you usually pick a row. It doesn't actually even matter what row or what column, but you pick a row and you expand across it. And what I mean is you take each coefficient. So if I expand this across the first row, you take each cell and you put that out front, and then you deal with a smaller sort of submatrix, right? So we can do 1 times the determinant of everything that's left. You just kind of annihilate everything in that row and column. So we'll get 1 times, and then the determinant of this matrix. 1, 0, 2, 6, 7, 8, 7, 8, 8. Then you got to be careful, because as you move to this entry, you're going to alternate sign every time. So you go plus, minus, plus, minus. It's like we have this grid underneath with alternating symbols. Anyway, you need this positive or negative 1 coefficient when you do this expansion. It's important, or else you get the wrong number. And that's like the bulk of what I remember about determinants, to be honest. You can see even up here, like I didn't have a great explanation for you for why adding a row to another row does not change the determinant. Always kind of blew my mind, but I'll bet if I was like knee deep into the theory, it would be obvious again. But anyway, let's finish my thought. So if you're expanding across this row, you get positive 1 times the determinant of the submatrix. Then you get negative 2. It's very important you don't skip that negative sign, right? Negative 2 times the determinant of, and this is going to be everything that's left when you eliminate that column and that row. So we're going to be left with 0, 0, 2, and 4, 7, 8. We skipped the 6 that was there. And 5, 8, 8. We skipped the 7 that was there. Okay, then we have to finish the row. We move on to the 3. But this time is positive because it alternates each step that we go. So we get plus 3 times the determinant of the, I forget what the name of this is, but I keep calling it the determinant of the submatrix that's left. So in our case, 0, 1, 2, 4, 7, 8, 5, 8, 8. And then because we're on this term now, we went plus, minus, plus, minus. This 4 needs to have a minus in front of it. And it's going to be minus 4 times the determinant of this guy whose name I don't remember, but the submatrix that's left when you annihilate the first row and fourth column, you know, the row and column that are associated with this entry. So it's negative 4 times this submatrix that's left when you get rid of that row and column. So in our case, it's 0, 1, 0, 4, 6, 7. So that's enough of my babbling. We can go back to the actual question that I had. Let me zoom in on it for you. The thing is, if you haven't thought about it already, you want to expand. You know, I wish these were zeros because I hate doing math. I want as many zeros as possible. Like if it were, so back in this example, I should have expanded across the second row because there's 2 zeros right there. That gets rid of like half my work, right? So think about that as you're staring at this. Well, you can probably see it, right? I'll just do this. You want to expand across either the first row, that's a fine choice, or you could even expand across the last column, because there's 2 zeros right there. That's my instinct. If you were going to do no other work, you should at least do that. You should at least just expand across the first row, because those 2 zeros are going to make your life a little easier. Or even the last column is fine too. So you'd get 8, or hold on, plus, minus, plus, minus. Okay, so you get negative 8 times the determinant of this junk. I'll write it down in a sec. And then you get plus this, what, great, it's 0, so we don't care. Minus this, also 0, that's awesome. And then what, minus, plus, you get a 4 times the determinant of this stuff. Well, I'll write it down. Oops. So I did this previously. I can show you my answers. But I think what I probably did first before I do anything is I probably like row reduced a bit. Like I probably tried to introduce more zeros because that's how much I hate multiplying and adding things. So I might have tried to like eliminate this 3. I'm not sure. Maybe I'll do it a different way today. But let me show you what I thought before. If I add row 2 to 3 and 4. Oh, you can't see it. Hold on, let me pull it up. Add row 2 to 3 and 4. Why would I do that? Oh, I see. So yeah, I noticed that if I add row 2 to row 4, it kills off this 7. That's what I noticed. I noticed there's a -7 here and a 7 there. And I was like, oh, let's kill this 7. What else? Rows 3. I mean, it makes the numbers smaller. You see how it gives you 4. If you add this to this, if you add row 2 to row 3, it gives you 4, and then 1, and then 1, and then 0. No, I'm just coughing. So it looks like I took it to this, and then I expanded across the first row. But that's really not necessary. I don't know. I was just trying to like make the work easier on myself. I don't think that was super necessary. Thank you, book. So let's forget about that. Let's suppose you didn't know any of this stuff that I was saying before. All you know is how to take a determinant. You're not going to have a problem with this question. If we take, so here's our original. I'm going to need more room than this probably, but here's our original 2, 0, 0, 8. You could certainly expand along the last column if you prefer, because there's also 2 zeros there. But I don't know how. It doesn't really matter. I don't think that really helps. But I think when I was doing this, when I wrote the problem down, I was like, man, I wish these numbers were smaller. Like, who wants to multiply by 7? I'd rather multiply by 1. I don't know. We don't have to do it that way. So here we go. Let's take the determinant of this. You'll get, what's going on, Jose? So let's expand across the first row. We're just doing exactly what I did above. So 2 times the determinant of the stuff that's left. So 2 times this sort of submatrix, -7, -5, 0, 8, 6, 0, 7, 5, 4. I mean, so when we go to do this determinant, of course, I'm going to do the last column because I love these zeros. But let's get back to the story. +2, and then you're going to get -0 times some stuff, but who cares because it's 0. All right, so I'm going to skip it. Well, we'll write it down. Why not? 1, -5, 0. But it doesn't matter because it's 0 times this stuff. 3, 6, 0, 0, 5, 4. Then we got +0 times, again, 1, -7, 0. It basically skips this column, right? Maybe I'll write it down just so you guys can see. 1. Try not to screw it up. -7, 0. 3, 8, 0. So I'm expanding on this cell now. So we're eliminating this column. And then 0, 7, 4 will be the last row. But it doesn't even matter because it's just going to be 0 times whatever that determinant. So it is some determinant, but who cares? 0. And the last one is, let's see, plus, minus, plus, minus. So I should have a -8 times whatever's left when you annihilate this last column and this first row. You get 1, -7, -5, 3, 8, 6, and 0, 7, 5. So cool. The zeros kill those off. That makes my life a little easier. Starting to think, I mean, that one's not going to be nice no matter what you do. Yeesh. Yikes. Yeah. Well, whatever. Let's keep going. But when I do this one, I'm going to use this column. That's what I'm going to expand around to get the determinant. So I'm going to go plus, minus, plus. So that's a plus. We get plus, minus, plus going down like that. So when I expand here, I get +0 times this stuff. Anyway, here goes. 2 times, and now I'm doing this big determinant. But I'm saying I love these zeros, so I'm going to actually use that column. Rather than saying it's -7 times this, +5 times this, I'd rather just get a bunch of zeros. So we're going to try that. Positive, negative, positive. So we'd get 0 times 8675, but we don't even really need to write this because it's just 0. What is it? Plus, minus, plus. So, okay. So positive 0 times this stuff, negative 0 times, if you eliminate this row and column, you'll get negative 7, negative 5, 7, 5. And then finally, positive 4. So that is there. Positive 4, and then the submatrix that's left when you eliminate that intersection of the last column, sorry, the last row and the last column. So negative 7, negative 5, 8, 6. That's all for the first chunk, which was not as bad as I thought. It looks like we're getting 8 times this determinant. 8 times the determinant, negative 7, negative 5, 8, 6. All right, and then we'll move on. 0, awesome. 0, awesome. And then I got minus 8 times whatever the heck this is going to give me. Oof. All right, well, let's just do it, I suppose. I'm tempted to go down this column because I see that 0 there, of course. I'm tempted to either do the third row or the first column. But, you know, it doesn't really matter. So let's just not and see what happens. Well, what's going to happen is you're going to have 3 terms instead of 2. But, okay. So we get 1 times this determinant, 8, 6, 7, 5. We get negative of negative 7, so minus this number times the determinant of the stuff that's left when you eliminate the first row and second column. So 3605. And then positive, right? Plus, minus, plus, minus, plus. Okay, so positive of negative 5 times the determinant of the stuff when you eliminate, you know, the stuff that negative 5 has in common, the first row and the third column. So 3807. Well, that's not fun. This sucks. Yeah. Well, whatever. So 8 times this stuff minus 8 times, and then we just got to crunch the numbers, I suppose. So 8 by 5 is like 40. This is 40 minus 7 times 6, 42? Yeah, that's right. Plus 7 times, what is this, 15? 3 times 5 is 15, but you're doing 15 minus 0, 15 minus 6 times 0, right? So 15. And then minus 5 times 3 by 7 is 21. It's 21 minus 0, right? 3 times 7 minus 8 times 0. So 21 minus 0. Yeah, in my answer on the website, it worked out to be a little nicer for me. You see what happened? By me like adding a couple rows, I got a different matrix, and the numbers were smaller. And then basically I just expanded once, and it immediately was apparent. Because there's so many zeros, like it was obvious to me that the answer was 0. In our case, you know, this is really not obvious at all. You know, I still have a bunch of stuff to do. So 7 by 6 we said is what, 42? So this is negative 42. Ah, man, this is annoying. 8 times negative 42. 5 by 8 is 40, so you're subtracting the negative of 40. So you're getting negative 16 right there. This first chunk is negative 16. This next chunk is like, gross. Oh, those are the same number, aren't they? Those are 0. So it's not as bad as I thought. This is negative 2. This is basically 0, right? So 21 times 5 is like 105. So you're getting negative 16 plus 16 is 0. Anyway, since the determinant is 0, it is not invertible. And that's it for this particular question. Yeah, I was just, hey Fook, I don't know, it's a good question, why? I just wanted to see how bad it would be. So like, I wrote down the answer earlier, and the way I had done it was, sorry, here's our matrix. And I noticed that like, this 7 cancels that 7. It also turns this 8 into a 1 if you just add these 2 rows. So when I wrote up my answer, I immediately changed this matrix to have a lot more zeros. And then I took the determinant. And I didn't write out the next step, but you can see if you expand here, you're getting negative 4 times this. Wait, plus, minus, plus, minus, plus. Yeah, that's right. Oh, sorry, positive 4. So you're getting like 8 times this block minus 8 times this block, and they happen to be the same. So, you know, it's just a little easier. So it is certainly faster to add the rows first. But I wanted to see how bad it would be if I didn't think to do that, you know. So that was it for our linear algebra question today. That was an easy one, very computational. Previous linear algebras, let's see, last week's was, this one's actually also pretty computational, pretty straightforward. Really the hard part on these kind of questions is even just remembering this formula. But this one I always liked because it has some applications, you know. Like this almost seems like something you'll see in an economics class. I've seen it come up in like finite math classes. This Lontief input-output analysis, like business math. Sometimes they'll teach you this at the end when they talk about matrices. This comes up as an application. Sorry, let's see this again. Fook says, do minus 2 of row 4. Oh, yes, right. So you get another 0 there. Yeah, but then oh yeah, I see. You have a bunch of zeros at the end. Yeah, that's pretty nice. That's pretty nice. Of course, it changes these numbers. Yeah. All right, I am moving on. Let us move on to the abstract algebra question. And I'm almost done here. We're just doing through 59. So here's the next question I'm going to look at. And then there's a real analysis question. I'll see if I remember how to do this one. All right. The question is z squared cyclic? Depends on what you mean by cyclic, of course. But generally what people mean is, can it be generated by one element? Not just a finite set of elements or something like that. Z cross Z cyclic. So Z, of course, is the integers. If you're picturing it, you can just picture on the real line a bunch of, right? Sort of doubly infinite. So if this is 0, it goes off in both directions. The reason I bring that up is that if you were to just take a number like -1 or 1, you can cover this set by just taking any multiple, any integer multiple. It's a bit of a silly thing to say, isn't it? Z is generated by Z. But no, I mean, if you take this element 1, which is an element in the set of integers, you could even take just -1. Okay? So Z is cyclic. the integers under addition as a group is generated by 1 or -1. They both work to generate the whole group. And when I say generate, I mean you're taking any integer multiple. So the reason we have to choose 1 or -1 is you're going to be missing a bunch of points. Like if you look at the ones generated by 2, that's basically all the even numbers, all the negative even integers and positive even integers and 0. So you're missing all the odd ones. So you can't use 2 or really anything else. You have to use 1 or -1 to get the whole group. So the question here is kind of fundamental. If you look at z cross z, this is a grid now, right? So I don't know. It's a subset of the plane r squared. But yeah, now you've got this still sort of doubly infinite. But yeah, it's basically just all numbers like this where a and b are integers. I should have just said a is an integer, b is an integer. A comma b are integers. All right, so that's the set z cross z, or z square. Awesome penmanship I've got going on here. But again, I want to stress what most people mean when they say cyclic is that I should have one element. I should be able to put one thing here, like 1, 1, and have it generate whatever you're talking about. It generates a subgroup of this for sure, but is it possible to find an element where it generates the whole group z squared? And I think your instincts should be probably no, right? Because you would think it would have to be a 1, right? They would have to both be 1 or maybe 1 -1. That would be your instinct to try, because you don't want to miss anything, of course. You already know a problem with not choosing 1. So your instinct is like, let's take 1. Let's take 1, 1. But of course the problem there is you're not getting barely any of the group, right? You're just getting the diagonal. If you took 1, 1, you get this diagonal. If you take 1, -1, I guess you get this sort of off diagonal. Either way, can I like prove that to you? Let's see. If we look at this example, 1, 1 would be the set. Yeah, it's the same concept as this. So you have a single multiplier times your element, right? So you're just immediately getting k comma k, which is why I drew a straight line through 1, 1, 2, 2, 3, 3, 4, 4, etc. That's not good enough, is it? So that's the issue, is we've got sort of one variable of freedom, but you're looking at a two-dimensional object. If we do the same kind of idea down here, k times 1, -1, you're getting k comma -k. That's really not good enough. So the answer on this is no, it's not cyclic. And there's really not much to the proof. If you wanted to prove it, you'd say something like what I just wrote here, or something like this. Or if you really want to actually prove it, you would need to say something like, not 1, 1, but AB, right? If I take a set of all the points that look like k times AB, then the result is like this. And it's clear that this is just multiples of, it gives us a line of slope b over a, right? It gives us a subset of that line, but there's no way that that line is, it's not a two-dimensional shape. I suppose we could construct, like, we could say you're missing negative BA or something. Like you're missing, how do you want to write it? We can claim that like a comma negative b, despite being in z squared, is not an element of this subgroup that we just talked about, that we just generated. Okay? So all you would have to do is demonstrate that, like, zero, the origin is there, for sure, but, like, even if you pick 1, 1, we know that 1, -1 is not going to be in the set that you just generated. So that would be a proof that it's not cyclic. It's not cyclic in the sense that there's one generator. Now, once you allow me to have 2 generators, that's a different story, because then we can just, but that's not cyclic. That's not what it means to be cyclic. But if you did allow, there are 2 generators, right? You could do, if you took, like, not the union, but if you put 2 points in here, like 1, 0 and 0, 1, then yeah, you're going to be okay. Like, that's going to generate the whole set. But this is a different object. This is basically all points of the form, it's basically m comma n, where these are both integers. And yes, of course, that's z squared. You don't even have to use, I'm pretty sure you don't even have to use, perpendicular points like this. I happen to pick orthogonal points, but that's not, as long as they're distinct, you'll be okay, right? Anyway, I'm going to move on from that. That was my little abstract algebra question for the day. And the last question I want to talk about today, this has been a long session, but I guess that makes sense. I used to do just 5 problems at a time and it'd be close to an hour. But lately I've been doing like 10. I do like 10 at a time, and I do them once a month. Last question is a real analysis question. Actually, if you're interested in this stuff, you should sign up on the site and take a look at next week's question. Because the current question is actually a complex analysis one, if you're into that stuff. But I'm going to do this one in the next video. Like, what's the principal value of I to the I? Which is cool. I made this site and these questions so that I could brush up on undergrad math, so I don't forget this stuff. But it's really they're just homework questions. They're not meant to be like research questions or anything like that. All right, we're looking at 59, which is now a real analysis question. And I'll zoom in so you can see it. Maybe we'll talk about it real quick. So the terms are positive, strictly positive. That matters, right? Because when you take a partial sum, you know that this partial is increasing. I mean, yeah, it's actually strictly increasing. I guess if this was greater than or equal to 0, you could say it's monotonically increasing. So it would be conceivable that the partials stay equal. It's possible that S2 equals S3 equals S4. But that is not the case for our hypothesis. We're assuming that the terms are positive, strictly positive. That alone is not enough for it to diverge. You could have a geometric series, right? If the ANs were like 1/2 to the power n, that's something that decays fast enough that you can take an infinite series and it will be convergent. It might be, in the case of half, it converges to 1. To picture what I'm talking about, take half plus a quarter plus an eighth plus a 16th. It's a bit like if you had this length 1, right? If you go halfway plus a quarter of the way plus an eighth of the way plus a 16th of the way, you can see the limit of that sum. It's not infinite, it's 1. So anyway, these first couple, this first comment that you've got strictly positive terms, that alone is not enough to diverge. You could certainly come up with examples that are convergent. But anyway, nevertheless, back to the problem. Suppose you've got strictly positive terms, and suppose that your series diverges. And that's it for the hypotheses. The questions are, can you prove that this quantity also would be divergent first of all. Let's start with that one. If an is small, then this denominator gets large, right? It doesn't get larger than maybe that's not a super helpful thing to say. Because it's close to 1, right? As an gets closer to 0, the bottom gets closer to 1. If an was very large, on the other hand, then you're dividing by something just as large. It gets small. So if an was like huge, and that's the reason this is divergent, then you're getting a term like 1. And so it kind of stands to reason that this is still divergent. But that assumes that all the an's are very big. If instead they're smallish, does it seem like maybe you'd get 0? You'd get something small, and then dividing by like something bigger than 1. Seems conceivable that it's convergent, right? I don't know. Let's see if I can prove this one. So I happen to have looked at this before, otherwise I'd be here struggling. But I did think about this before. I think you want to look at it in two cases. One case would be that the AIs are I want to say greater than 1 infinitely often. If it's the case that AI is greater than 1, then this is greater than 2, right? And then, did I do this backwards? I might have it the other way that I want it. Yeah, I was trying to go the other direction with it. I'm trying to compare this series to the original series. There's two ways we're going to show that this is divergent. Either this is greater than a sum of like a fixed number, like half, or it's just comparable to the original series AN, which is also divergent. And if you're sick of my babbling, you can just click on View Submissions. You'll see my actual answer. But I'm going to try to recreate it here if I can remember what I'm doing. The reason I'm stopping is that like this is the wrong direction. I actually wanted this to go the other way. So I think if we had at the tail end of this series, our divergent series, the sums of ANs, if we had at the tail end of those, the terms are all less than 1, then 1 plus this is less than 2, and the reciprocal is greater than half. Like this, basically I just swap the direction of these. And then we're good. It gets divergent. So I guess I have this backwards. I wanted to say, but that's okay. We'll come back to this. Either the majority of them are less than 1. We get a divergent series. Otherwise, this happens, and then how do we deal with it? Yeah, I don't quite remember. If we go the other direction with this, all right, like what I had meant to say was instead, suppose that for the vast majority of the terms, infinitely many of the terms, AI is less than 1, or even equal to 1, for infinitely many terms. Then you can do what I just wrote, and you'll get a divergent series, okay? Then we can say that AI plus 1 is bounded by 2, and therefore its reciprocal is bounded from below by half, like that. And so this series, an over 1 plus an, is greater than half of just the an series. That's the numerator, right? And we know this is divergent, and therefore this is divergent. So that's the argument I was trying to make here. I just had it backwards. Suppose that infinitely many of them are bounded by 1, then we're done. The other case would be that many of them are bigger than 1. So we're looking at terms where they are frequently bigger than 1, right? I feel like you just dividing by this is not going to be enough to make it small, but I can't quite see it right now. If I add 1 and divide, I got the easy case done. This case, do I have to just compare it to now? Let me think. I'm trying not to look at my answers. So like what happens to here we were able to just compare to the original series. I basically just did a comparison. Here, what am I going to do with this? We know that the denominator is bigger than 2, so this is less than half, but I don't want to go less than. I want to be able to say that this is bigger than something. Oh, is it always bigger than half? The terms themselves, I'm saying. If this happens, then 1 plus an is bigger than 2, right? And so, no, damn it. What if I divide by this? We've got, so like this is the same series. If this happens, then 1 over an is less than 1. is this bigger than half? You see what I'm saying? I think we've got a lower bound for the size of the terms in this case, and it's not 0, and that's enough to say it's divergent. But I don't quite see it yet. I'm like circling it. So if for infinitely many of the terms this happens instead, I know this. I don't want an upper bound. I want it to say that. Oh yeah. This is the denominator. If I add 1, it's less than 2. That's it. So if this happens, this plus 1 is less than 2. You see what I'm saying? Damn it. No, that's right. That's what I'm doing. Good. And now take the reciprocal of this and we're done. This means the reciprocal. I don't even need these absolute values because they're positive terms, but I keep writing it. This is bigger than half, which means these terms that you're adding up in your series are bounded from below by half. There's no way this could be a convergent series. It fails the divergence test. Okay? If infinitely often your terms are larger than 1, then that means I actually didn't use this line. Okay? What I instead says was that means your reciprocal is less than 1, and if you add 1 to it, that means this stuff is less than 2. And now we take the reciprocal, and that looks suspiciously like these terms right here. Right? But this is also bounded from below by half. So you're adding up a bunch of things that are at least half in size. You can kind of see it, right? If you're telling me that infinitely often it's bigger than 1, what if it was a huge term? I was saying, well, then this would practically be 1. That's the extreme, that you'd be adding up a bunch of terms that look like 1. But you can see that there's an issue there already, right? Like that's what led me to this kind of thought that, oh, there's got to be like a lower bound. So if you're bigger than 1 at all, if your magnitudes for many of these, if you're adding up terms originally, our assumption was that the ANs are divergent. And then, of course, that they're positive. Those are our only hypotheses for this question. But anyway, if you know that this is divergent and you're telling me that most of the time these terms are bigger than 1, then when you look at stuff like this, you're looking at like 2 over 3, right? Or you're looking at like 1.1 over 2.1, right? That's about half, isn't it? This is as small as it could get. So you can see if you had thought about this question, if you thought about this hypothesis with some real numbers in this ratio, you can see how you get half. Like half is clearly the lower bound. There's a boundary here. There's a minimum that these terms can be. So if infinitely many of them are at least 1, when you take this ratio, you're looking at stuff that's at least half. That's where this came from. I mean, that's the sort of logic. If you were just sit here and wonder where to start, you could just start plugging numbers in. Like, okay, what if the AI is 2? What if the AI is 1.1? And you'll eventually see that like the smallest this ratio could be is half. That wouldn't really help you get to here, because this was just algebra. But that would at least give you like a path to say like, oh yeah, this is divergent. This is probably something I can say to prove that this is divergent. All right. Back to the question. So that was part 1. The rest of it's not as bad, if I recall correctly. It looks nasty, but it's not. The first one was actually the hardest one for me. Second one says, prove that the sum of these terms, okay, we're basically just going to prove that this diverges, is the question. Prove that even if you took your terms and you divided them by the partial sum, that would still be not enough to temper this thing to make it convergent. So even this is divergent, where the S represents the partial sum, the partial series, terms 1 through n. So yeah, somehow, I think it relies on the ANs being strictly positive. I think that's going to be part of our argument. But yeah, even scaling back each term by the partial series That certainly makes the terms smaller, but it does not make them small enough to be a convergent series, not in general. Actually, not ever. Not ever, evidently. I was thinking maybe we can get a counterexample, but no, you're not going to be able to. But this one's not as bad. So first we want to show this inequality. But then if we had this inequality, then you're telling me that the partial sum of this series, that's this term on the left-hand side, that partial sum is bounded from below by this junk, which looks like it's going to tend to some positive number. Let's see, partial sum. Oh, that's not just the partial sum. Sorry. That's not just the partial sum. That's actually the I don't know what it's called. I always call it like the Cauchy remainder, but that's not what it is. The tail end of your sum. If you start at n and you add up all the terms after that, that's like the tail end of your sum is always bounded by some positive thing. That would be enough to show it's divergent because it's not a Cauchy series. So yeah, what are we doing here? First, we want to show this inequality. It's actually not bad. The right-hand side looks like this. This is the same thing as the right-hand side, right? This is just 1 minus Sn over Sn plus k. So that's the right-hand side. The numerator then is partial sum up to n, partial sum up to n plus k, minus the partial sum up to n. So we'd be starting at the n plus first term, and we'd be adding n plus 2 all the way up to a n plus k. That'd be our numerator. And the denominator is still the same, partial sum all the way up to n plus k. So this junk is our right-hand side. Notice that here, you're dividing by Sn plus k on every single term. But our left-hand side, you're dividing by sort of the corresponding guy, not just this term, but you have an plus 1 over Sn plus 1, and an plus 2 over Sn plus 2, right? Oops, an plus k over Sn plus k. This is actually greater than or equal to this stuff. And the reason is Sn plus k is bigger than, like this is definitely bigger than the n plus 1 case. It has more terms in it. And like, so if you put Sn plus k in all these denominators instead of their corresponding ones, like, the point is, this is true because this last thing that I wrote, the left-hand side is greater than the right-hand side. It's true because the SNs are actually strictly increasing. So for instance here, Sn plus k, it's bigger than or equal to Sn. Actually, it's strictly bigger than in our case. It's strictly bigger because all the terms are strictly positive. But anyway, it's bigger than Sn plus k minus 1, which is bigger than Sn plus k minus 2, which is bigger than, etc. Bigger than Sn plus 2, bigger than Sn plus 1. So when you take basically this reciprocal, 1 over Sn plus 1, that part, it's bigger than 1 over Sn plus k. And 1 over Sn plus 2, that's bigger than 1 over Sn plus k. So it's these denominators changing, the fact that these denominators are always strictly bigger than those denominators. So this right-hand side is smaller than the left-hand side. So that's actually pretty easy to prove that inequality. That was step 1. The second part is a little trickier. It has to do with Cauchy series, I guess. What we're going to do for the second part, we've just realized that the sort of tail end, the tail of your series is bounded from below by this formula, 1 minus Sn over Sn plus k, right? I basically just want to take a limit and show you that this never goes to 0. This doesn't go to 0, which does not tend to 0 as n gets big. If it did tend to 0, then we'd be able to say, oh, that's a Cauchy series. Like that series is convergent because the terms were Cauchy. You know what I mean? The sum of the tail, you can, its limit is 0. That would be enough to say it's convergent. But it's not convergent because it's bounded from below by this. So now I'm going to have to make some sort of argument to explain why this does not go to 1. You can choose k. K is definitely, it's not bigger than n, but n plus k is bigger than n. K is positive, and k can be whatever you want. When you take this limit, you're letting, like I'm basically saying we need to show that the limit as k and n go to infinity of this is not 1. If it were, we would, that would be bad, right? That would mean it's convergent. If it were 1, then it means it doesn't matter how much further out you go. At some point, these things stabilize to the same value. The sum that stops at n and the sum that stops at some arbitrary point after n eventually becomes the same. That would be enough to say we're looking at a convergent series. But we're not looking at a convergent series, so apparently this is true, right? Why is this true? Well, the reason is actually, I guess I didn't write it down, but I've used it here. I said it here. This is true because the partial series are increasing, strictly increasing. It's true because of this hypothesis that the terms are positive. They're strictly positive. So every time you move from Sn to Sn plus 1, S increased. It went up. It's actually strictly increasing. So what I'm saying is, given an n value, choose k so that Sn plus k is greater than 2 times Sn. We know you can do that because the original series is divergent, and they're all just strictly positive terms. So I know that this is actually just growing without bound. So eventually it'll be twice the size that it used to be, right? So that's what this says, that choose k so that we are twice the size we used to be. And what that means is your ratio Sn over Sn plus k is less than half, right? It might even be equal to half, but that doesn't matter. So this ratio is less than half. If you, let's see, here we are. If you subtract it, you'll have something bigger than half. You then add 1, or sorry, bigger than negative half. My point is, once you have this inequality, you can show that this is bigger than half, which means it's definitely strictly bigger than 0, which means we're done. It's divergent. So once this happens, then the negative of that is bigger than negative half. And if you add 1 to this, you'll have that right-hand side that we've been talking about. So you'll have shown that the tail of your series, this series, the an divided by Sn series, the tail of your series is bounded from below by this. And this is bigger than half. And so the tail of your series does not shrink to 0. That means your series is not Cauchy. It means your series is not convergent. So that's the end of 2. And then 3 says, prove that if you divide by the sum squared, that actually basically is enough to get you a convergent series. So this time we're going to show that if you take your terms and you divide by the partial sum squared, that's a little different. Suddenly that's enough to temper this term small enough that the infinite sum does converge. Kind of impressive. But it's coming from this. It's coming from this. This is actually, so let's prove that inequality. First of all, how do you write that right-hand side? If you were to just add those fractions on the right-hand side, you'll get partial up to n minus partial up to n minus 1. You divide by the product, right? Sn times Sn minus 1. So this is the same as the right-hand side. This is subtraction upstairs. This is just a product downstairs. So this is the right-hand side of that inequality that you're looking at right there on number 3. Notice, again, this series is strictly increasing. So if I were to divide by Sn instead of Sn minus 1, what does that make it smaller? So this is bigger than the same series, sorry, the same expression, but if I replace this Sn minus 1 with just Sn, it'll get smaller because Sn is bigger than Sn minus 1, right? So this is true. And I think that's what we're looking at. I think that's it for the inequality, right? This numerator is an, and the denominator is Sn squared. So we just proved the inequality. And how does that help us? Well, that's an actual term. What we're looking at here is one of the terms in the series like this. That series, this is one of the terms. They're telling us that this term, so if we were to write out well, here's what I mean. I should say it's bounded by. This is less than the series that you would get if you just added 1 over Sn minus 1 minus 1 over Sn. Okay? So we just proved that this is less than that. So we know that the series for this is less than the series for that. But this is a telescoping series, isn't it? So if you let n be, let's start at 1 just so there's no confusion. If you start at 1 here, oops, the right-hand side is telescoping, right? The right-hand side looks like it says 1 over S0 minus 1 over S1 plus 1 over S1 minus 1 over S2 plus 1 over S2 minus 1 over S3. Yada, yada, yada. These are canceling, aren't they? Right? Everything's canceling. What you're getting is 1 over S0 minus 1 over Sn. Sorry, I should... If you're going to take the limit here as n goes to infinity, then here you'll get a limit as n goes to infinity of 1 over Sn. And since the Sn increases to infinity, this limit is 0. So you're just getting 1 over S0, which of course is also just A. It's 1 over A0. So this is bounded by, I'm not saying this is equal to 1 over A0, but it's bounded by 1 over A0 because it's bounded by this telescoping series. And that is it for number 3. And that is it for today's session, ladies and gents. Thank you all for tuning in. Again, these answers are on the website, but they're shorter, you know. I don't know. I try to be a little more wordy with my explanations in these videos. But I did write this down, so if part of what I said here, or you don't want to if you don't want to go back through the video, you can just look at my submissions on the website. I try to post answers lately it's been about once a month. So usually every time I have 10 new problems, I post a video with my solutions, explanations. But I try to post answers, you know, once a week or so. Anyway, thank you all for tuning in. Have yourselves a great day. And ta-ta for now.